let's take a look at discussion 5.11 here. A crate of books rests on a level floor. To move it along the floor at a constant velocity, why do you exert a smaller force if you pull it at an angle theta above the horizontal than if you push at an angle below the horizontal? Okay, so if I think about this, if I push at the same angle above and below, I'm getting this component here. And this component has to match the frictional force in order for it to pull at a constant velocity. Now, if I'm pushing down, I have a component that is adding to the weight, so it makes my normal force larger, which makes my frictional force larger. So I need a bigger overall force to get that horizontal component to match that frictional force. Whereas if I pull up at an angle, the normal force becomes less, and as the normal force becomes less, the frictional force becomes less, and so I need a less overall force to match. So that's the answer. We're going to go a little bit more in depth here since we're in a video, and I'm sure the view numbers are going to go through the roof when we do this. So the sum of the forces is going to equal 0 in my x direction. Okay. The sum of the forces in the y direction is also going to equal 0. We're just going to assume the mass is large enough that our force isn't going to yank it off the table. Okay. So we have the force times the cosine of our angle, where our angle is here, is going to have to equal the force of friction in order for this to be true. So F cosine theta minus force of friction equals 0. So they got to be equal to each other. So I have F cosine of theta equals mu times the normal force. I'm going to need to solve for the normal force here. So I have normal force plus F sine theta minus mg equals 0. So I should be able to solve for the normal force being mg minus F sine theta. Bringing that over here. So now I have mu times mg minus F sine theta. Let's get all of those forces on the same side. So we're going to distribute the mu and bring that over. So I have F cosine of theta plus F times mu sine theta equals mu mg. Factor out our force and divide. So I have F is equal to mu mg divided by the cosine of theta plus mu sine theta. Why did you do that, Mr. Foster? I did this because this equation allows us to think about what angle is going to work best. So graphically, this is going to look something like this, where this is my 90 degrees, at which point it's no longer going to work. So I'm bounding this solution to 0 to 90 degrees. And so there is going to be an angle in here that is going to require the minimum force to pull. Now, in order to find that angle, you of course would simply take the derivative of such equation, set it equal to 0, and solve for what that angle is. You're welcome to do that on your own time. You will find, though, that this angle is dependent on mu. So as your mu changes, this curve changes, and so that angle also changes. But in general, as long as you give it a little bit of an angle up, it is going to be easier to pull as you start to increase that angle above the horizontal. There's a little side note for you there.